So, welcome back. In the last few lectures, we have started the Fourier transform, Fourier cosine transform and Fourier sine transform. We have seen the properties of the Fourier transform, Fourier sine transform, Fourier cosine transform, and if I know the Fourier transform of a function, then the derivative Fourier transform of the derivative of the functions we have seen. Also, we have seen the how to find out the Fourier transform of integration of a function like this, and using the properties and all these things, how to find out the Fourier transform of various functions. In this particular lectures, let us go through some more examples, so that you can understand much better way how to find out the Fourier transform or Fourier sine transform or Fourier cosine transform of a function, or if I know the Fourier transform of a function, then using the inverse Fourier transform, how to find out the Fourier transform, how to find out the function, that also we find out. So, let us see the first example. We want to evaluate the Fourier cosine transform of x to the power n minus 1, where x lies between 0 to 1. And once we are finding the Fourier cosine transform of x to the power n minus 1, then from here we have to show that 1 by root x is self reciprocal under Fourier cosine transform. If you remember, self reciprocal means the Fourier transform, Fourier cosine transform of the function 1 by root x will be 1 by root alpha itself, that is the function itself. Then we call it as a self reciprocal function. So, let us see this one. We know that the Fourier cosine transform of x to the power n minus 1, this is equals to, from definition, root over 2 by pi 0 to infinity x to the power n minus 1 into cos of alpha x dx. So, from definition, say this is equation 1. From definition, you are writing Fourier cosine transform of x to the power n minus 1. This is equals root over 2 by pi 0 to infinity x to the power n minus 1 cos of alpha x dx. If it was Fourier sine transform, then it would have been root over 2 by pi 0 to infinity x to the power n minus 1 sine of alpha x dx. Now, we have to evaluate this particular integral. There are various approaches to find out the value of this particular integral. I am telling you one another approach to find the solution or to find the value of this given integral. If you look here, x to the power n minus 1 is there, into cos of alpha x is there. So, if I try to find out some function of e power, which can be extended in the form of cos x and sin x, so that and whose value is known to us. So, let us start with, we know this thing gamma n, this is equals, from definition of gamma function 0 to infinity e to the power minus y, y to the power n minus y, n minus 1 into dy. We know this thing gamma n equals 0 to infinity e power minus y, y to the power n minus 1 into dy. Here substitute y equals, say, I alpha x. If I substitute y equals I alpha x, then you will get it 0 to infinity e power y is I alpha x. So, e power minus I alpha x into, this will be x to the power, y to the power n minus 1 is there. So, this will be x to the power n minus 1 di, dy will be changed to dx. So, gamma n by substitution I alpha to the power n, because here it is I alpha to the power n minus 1 is coming and this I alpha is there. So, it will become gamma n by I alpha n. So, I think it is quite clear that 0 to infinity e power minus I alpha x into x to the power n minus 1 dx, this is equals gamma n by I alpha whole to the power n, where we are substituting y equals I alpha x. So, that this again you can write down 0 to infinity e power minus I alpha x, you can write it in terms of cos function and sin function. So, that this is nothing but cos of alpha x minus I sin of alpha x into I sin of alpha x into x to the power n minus 1 dx. This is equals gamma n into I to the power minus n, I am just putting it here, and divided by alpha to the power n. So, you see now it is quite understandable that why I started with the gamma function, because gamma n is this thing, and which ultimately by this substitution y equals I alpha x equals, I am writing 0 to infinity cos alpha x minus I sin alpha x. And if you closely look this left hand side integral, if I take the real part of this integral, real part is nothing but 0 to infinity cos of alpha x into x to the power n minus 1 dx. The real part of this integral is this, and which is the required integral which I have to find out over here. So, for this reason we started from this gamma function and we are coming to this. Now, we have to simplify this function. So, this equals, therefore, in the next one I can write down 0 to infinity cos of alpha x minus I sin of alpha x into x to the power n minus 1 dx. This you got gamma n into I to the power minus n by alpha to the power n. This equals, you can write down gamma n, we are not doing anything, alpha to the power n, and this I can write down in the form of cos pi by 2 plus I sin pi by 2. This is quite clear. I always we can write it as cos pi by 2 plus I sin pi by 2. So, that the first part vanishes of the cos function and second part of the sin function is 1. So, this to the power minus 1. So, once I am writing this using again the theorem, this is nothing but this n can come here. So, it will be cos n pi by 2 minus I of sin n pi by 2. This directly we can write down, cos pi by 2 plus I sin pi by 2 whole to the power minus n. This we can write as cos n pi by 2 minus I into sin of n pi by 2. So, once I am getting this, therefore, equating the real part, you can write down 0 to infinity cos of alpha x into x to the power n minus 1 dx. This is equals gamma n alpha to the power n into cos of n pi by 2. So, you see, simply by using this one, we are obtaining the result of this integral. So, this is the beauty of this particular example, that it is not that I have to evaluate the integral in classical method, but I am using some integral whose value is known to me from the gamma function, and from the gamma function the e power part I am using, and which I am breaking it in terms of cos and sin, and ultimately by equating the real part I am getting the value of the given integral. So, the first part is over, that is 0 to infinity cos of alpha x into x to the power n minus 1 dx equals gamma n into this. So, that you can write down Fourier cosine transform of x to the power n minus 1, this is nothing but root over 2 by pi into gamma n by alpha to the power n into cos of n pi by 2. This is the required result. So, from here you see Fourier cosine transform of x to the power half minus half, or in other sense I can write it as let us not write down like this, Fourier cosine transform of 1 by root x I am writing. So, here basically you have to substitute n equals half, nothing else. You will put n equals half in this particular given equation. So, if you write down, it will become root over 2 by pi into gamma half divided by to the power half, means this will be root alpha into cos pi by 4, n is half. So, it becomes cos of pi by 4. So, if I substitute the values of gamma half, that is root pi, if I substitute the values of cos pi by 4, that this root 2 and this root pi will be cancelled, and you will obtain the result as 1 by root alpha. So, you see here Fourier cosine transform of 1 by root x, this is nothing but equals to 1 by root alpha. Therefore, the function 1 by root x is self reciprocal under Fourier cosine transform. So, please note that whenever some integrals are given, using the known results, if I want, I can find out the solution, or I can find out the value of some other integral also. Let us see quickly here, just we are doing it. Fourier cosine transform of x to the power n minus 1 is root over 2 by pi 0 to infinity x to the power n minus 1 cos of alpha x dx from the definition, and where we know that gamma n we know as 0 to infinity e power minus 1 minus y to the power n minus y dy. If you substitute here y equals I alpha x, your given integral will become 0 to infinity e power minus I alpha x into x to the power n minus 1 dx equals gamma n by I alpha whole to the power n. So, that your x to the power n minus 1 has already come here, and you have to find out only cos of alpha x. So, that e power always can be broken or can be written in terms of the cos and sine function, just like in the next one. E power we are writing as cos alpha x minus I sin alpha x into x to the power n minus 1 dx equals gamma n into I to the power minus n by alpha to the power n, as I told you earlier. So, that if I can find out the value of the right hand side equating the real part, I can obtain the value of my given integral, and in turn I can find out the Fourier cosine transform of x to the power n minus 1. So, this I now we are writing in the form of cos pi by 2 plus I sin pi by 2. So, that using complex properties I can write it as cos n pi by 2 minus I sin n pi by 2, because actually cos of minus n pi by 2 plus I sin minus n into pi by 2 is there. Then the properties, using the properties I can write it as cos n pi by 2 minus I sin n pi by 2. Therefore, equating the real part on the both side, I can write down 0 to infinity x to the power n minus 1 cos of alpha x dx. This is equals gamma n into cos n pi by 2 divided by alpha to the power n. Once I have obtained it, then I can always tell Fourier cosine transform of x to the power n minus 1. This is equals root over 2 by pi gamma n by alpha to the power n into cos of n pi by 2. So, once I obtain this value, I have to find out the Fourier cosine transform of 1 by root x, which is nothing but n equals half. I have to substitute in this Fourier cosine transform of x to the power n minus 1. So, by putting n equals half, I am getting root over 2 by pi gamma half by 1 by gamma half by root over alpha into cos pi by 4. Now, substitute the value of gamma half and cos pi by 4, and these terms will be cancelled. Root over pi will come for gamma half, cos pi by 4 1 by root 2. So, once they are cancelling, you are obtaining 1 by root alpha, and we can say from here that the function 1 by root x is self reciprocal with respect to Fourier cosine transform, because we are obtaining the same function as the Fourier cosine transform of this. So, I hope the self reciprocal concept is also clear. So, that thing only we have written. Now, let us see the next example. I want to find out the function f x, that is, now I am talking about the inverse function, means I know the Fourier cosine transform of a function. I want to know what is that function f x whose Fourier cosine transform is 1 by root over 2 pi a minus alpha by 2, because that will be a function of alpha. When alpha less than 2a and alpha greater than equals to a, it is 0. Or in other sense, the Fourier cosine transform is there from 0 to 2a only. 2a to infinity, the value of Fourier cosine transform of the given function f x is 0. So, using Fourier cosine transform, inverse Fourier cosine transform, we have to find out the value of f x. So, for this one your function is just we are writing Fourier cosine transform of alpha. This is equals 1 by root over 2 pi a minus alpha by 2, where alpha is less than 2a and this is equals 0 whenever your alpha is greater than equals to a. So, what is your f x? Your f x is equals to, from the definition, this is nothing but root over 2 by pi 0 to infinity Fourier cosine transform of alpha into cos of alpha x into integration will be on d alpha. So, that after putting the limits, this will be a function of x only. So, once I am writing this using the Fourier inverse Fourier cosine transform, please note that. So, here the problem is the different. I know the Fourier cosine transform, I have to find out the function whose Fourier transform is this one. So, I am using the inversion formula. Using inversion formula, we are writing f x equals root over 2 by pi 0 to infinity Fourier cosine transform of cos of alpha x. So, once I have obtained this, now I know Fourier cosine transform of the function is 1 by root over 2 by pi a minus alpha by 2 when alpha lies between 0 to 2 a only. So, that you can write down this one as root over 2 by pi 0 to 2 a 1 by root over 2 by pi into a minus alpha by 2 into cos of alpha x. So, this is quite clear. I think that whenever I am writing it 0 to 2 a in for 2 a to infinity, the value of the Fourier cosine transform is 0. Therefore, this integral will be coming as only this one. So, your f x equals, I can write it as 1 by root over 2 pi. So, root 2 will be cancelled, root pi 1 by pi is coming 0 to 2 a into a minus alpha by 2 into cos of alpha x, and you can find out the integral very easily. So, up to this I think it is fine that f x equals 1 by pi 0 to 2 a minus alpha by 2 into cos of alpha x dx. So, that if you evaluate the integral, your f x you can write down 1 by pi into, for the first part you can obtain a minus alpha by 2 into sin of alpha x by x, where alpha will vary from 0 to 2 a plus 1 by 2 x into 0 to 2 a sin of alpha x d alpha. So, using the earlier one, we are getting a cos alpha, we are writing it as this one a minus alpha by 2 into sin of alpha x. That means, we are using the first part integration by parts. Using integration by parts, you can write down this one. So, if I put the limits, the first part will be 0 for alpha equals 0 and for alpha equals a, for alpha equals 2 a, if I put then a minus 2 a by 2 will come, and this value will be